About 2.5 weeks ago, it was a Friday, I had a bad day, a really bad day. I had to prepare a lecture that I was going to give on Sunday. It was to the commercial users of functional programming, and I'd very foolishly put up a title, How to Make Money from Functional Programming. People thought that because I'd invented Erlang and because WhatsApp was written in Erlang, that WhatsApp was sold for $19 billion, I knew how to make money. But so here I was with this silly title. And I'd taken Friday off to be at home because I can't get any work done at work because you get interrupted all the time. And I started OpenOffice, and a little prompter came up and said, there's a new version of OpenOffice. Oh, great. So oh, that's good. It'll be better. So I clicked on this little thing. And yeah, what happened? Yes, I installed OpenOffice, and I started writing my site. I put some images in it, and suddenly all the images vanished. Oh, goodness. And I wasn't really pleased about that. And so I Googled a bit, and it said, oh, OpenOffice can lose images under some strange circumstances. This was reported several years ago. It's still there. And so I thought, oh, golly, what do I do now? Well, Apple had very kindly broken Keynote as well for me, because I had my workflow. So I have a MacBook Pro, big one, 17-inch, whatever it is, heavy. And I do all my slides there. And I put them into Dropbox. And then I have a small 11-inch Air machine there. And then when I finish my lecture, I close the lid. And I open the lid on this thing, and it syncs up. So Apple had very kindly put different versions of Keynote on one machine and the other, so that the things I saved on one couldn't be read on the other. They've completely destroyed my workflow. So I wasn't very happy about this. And so I thought, I know what I'll do. I'll do my slides in HTML. You've seen these slideshows that are in HTML. Yeah, they're really nice. But there's one problem with them, that people like to get PDF copies of the slides afterwards. And so most of these slideshows that people have done in HTML don't produce decent PDF. So if there's anybody out there who's written one of these, please make it produce decent PDF. And so I Googled a bit, and I found a project that said, you can make nice slideshows in HTML, and they can produce decent PDF. And so I downloaded this program, and I followed the instructions. And it said I didn't have Grunt installed. Now, I'm an old guy, so I didn't really know what Grunt was, and my Grunt files weren't right or something. So I Googled a bit, and I found out what Grunt was. Grunt's, I still don't really know what it is, but... So I downloaded this thing, and I installed Grunt, and it said Grunt was installed. And then I ran the script that was going to make my slides. And it said unable to find local Grunt, but I just installed Grunt. So I turned to Twitter and tweeted, I'm having a really bad day here. It's unable to find the local Grunt. And Twitter is very helpful, because people said, well, your Grunt path is incorrect. Set your Grunt path. And I set my... So I gave up. So that was it. Right. So you'll get to the title of the talk in a while. I've been programming since, golly, a long time ago, 1965, something like that. That's quite a long time. And programming actually goes back longer than that. The first computer program that is remotely reminiscent of the way we write programs today ran on June the 21st, 1948. And it was written by Tom Kilburn. That's Tom Kilburn. He is the world's first... I know they say Ada Lovelace was the first programmer, but she didn't program the sort of machine we program today. This is Tom Kilburn holding a Williams memory. That was the thing that enabled programmable machines. It can store, 64 32-bit words, right? That was the total storage. And it's a cathode ray tube. So as the store is changing, you can see on the display what was going on. And this was the first program that was ever written. It was, that was it. And it ran I've forgotten the date, in June 1948. And the nice thing about that program, it was probably the last program that was totally correct. I mean, there's just one program in the entire world. This is the first program that you put the program into memory and you can change the instructions and then they're executed. And it computed, I think it checked the first 38 prime numbers or something like that. And they're all very pleased that it worked. Of course, they didn't realize what they'd done. And I don't think Kilburn thought that, just imagine, he was programmer number 1. That's kind of cool. Right. Why am I talking about that? Well, let's go roughly halfway between 1948 and today, 1985. This is when I started work on Erlang. And at the time, a computer looked like this. This was a really powerful, fantastic, super-duper machine. Typical PC, it's got 254 kilobytes of memory. Isn't that a lot? And amazingly powerful 8 megahertz clock speed. That's pretty cool. You can do amazing things with that. Yeah, it was great. So if we look at today's computers, this is a typical laptop. It's got 8 gigabytes of memory, so it's 32,000 times much more memory than that little thing had in the mid-'80s. It's got 4 cores running at 2.5 gigahertz. That makes it about 1,000 times faster. It's got a big solid-state disk and so on. Now, in 1985, that machine would boot in, 60 seconds. And this machine is 10,000 times faster or 1,000 times faster. It should boot in about 60 milliseconds. How many of your machines boot in 60 milliseconds? Right, so something's gone wrong. Where did it go wrong? Okay, so that's the title of my lecture, The Mess We're In. I'm going to look at the things that I think are going wrong, and I talk a little bit about why they're going wrong. And then I'm going to talk about the physical limits of computation. So I'm going to relate the speed of computers to some physical quantities, so we can just see kind of ballpark where we're in. And then I'm going to suggest some ways that we might be able to clean up this mess. Okay. I think software is actually getting worse and worse and worse with time. It's not that we can't do amazingly good things with computers. Of course we can, but when they don't work, we don't understand why they don't work. Okay. In the past, you see, I'll go back about 30 years ago, if you had a program and you didn't understand why it didn't work, you could look at it. And now when you've got a program that doesn't work, you don't look at it, you ask Google, why doesn't my program work? And then, of course, it says, well, try this, and it'll make it work. You try it, and it doesn't make it work. And I'm going to explain why that is, because I was thinking about that a bit. Right, so my generation of programmers, I think we should get big medals. We should get the Congressional Medal for Creating Employment, because we have created billions of man-hours of maintenance work for people in the future. We are the job creators of the future. All that stuff we wrote years ago, these poor sods will be scratching their heads and going, what the hell does this stuff do? And it's terrible. Right, so what went wrong? I'm going to talk about that. And what are the laws of physics? Because I used to be a physicist, so I'm going to tell you about black hole computers and things like that. Right? If we can make them, they would be quite good. Okay, so when I was preparing this, I thought, I know. I was going to show pictures of Gustave Doré's Dante's Inferno and, the levels of hell and all that kind of stuff. And I thought, well, I'd write down 7 deadly sins. And I was doing this on the Underground. And I tweeted. I got, by the time I had to get off the Underground, I'd written down 25. And I had some trouble in sort of ordering them. If you look at these, code, one thing I notice is code that I write now, which I can't understand in a week's time. Do you do that? Am I unique in that? I write some code, I really understand it, and a week later I can't understand it. How many people do that? Oh, good, I'm not alone. I just thought it was only me. I think that's because your brain works in 2 different ways. It sort of, when you're working on a program, you're like cached into the program, and you see no need to explain it to anybody because it's bloody obvious, so you don't write any documentation. And when you've cached it out, you wish there was some documentation because you can't understand it at all, right? So this is very difficult. So the answer to this is comments. And if you look at these sins, no comments in the code, you can't understand it, no specification, very obscure, it's not beautiful. That's all about shifting your brain from the mode you're in when you're writing code to the mode you need to be in when you're explaining how the code works. Right. So has anybody heard of comments? Does anybody put comments in their code? Right. Does anybody put no comments at all in their code in modules? Right, yes. Yes, I've done that. A lot. Robert Veerding, who developed Erlang with me, was famed for his comment. I think he only wrote singular. The entire stuff he wrote had one comment in. In the middle of the pattern matching compiler, there was a single line that said, "And now for the tricky bit." Which I thought was quite good. Now, comments are really good. So I would advise you to write comments now. And write big comments. Right? Really big, really exclusive comments. Now, how many people write really big comments? Right. Well, I was going to say, there's another word for a really big comment. What's that? No? A book. How many authors have we got here? Well done. Thank you very much. Because if you haven't got a book, you don't know how the bloody program works. Right? So a book's just a big comment. Right? And it's difficult at first. Just write your comments, and they're bigger and bigger and bigger, and pull them out and stick them in a book. And once you've published the book, you'll be rich and famous, and they'll invite you to conferences, and you can talk about your book. We'll forget about the rich and famous bit. You can talk about your book anyway. Right. Okay, so we've done all these deadly sins and things, and there's a load more. And then today we've got this stuff, legacy code, to deal with. What's legacy code? Well, that's dead programmer stuff. I mean, not only are there no comments in it, you can't ask the people who wrote it because they're dead. And it's written in languages that nobody understands, written in COBOL. And there's no specification, and yet it works beautifully. Possibly. And management thinks that modifying legacy code is cheaper than a total rewrite. I can tell you, I've looked at some legacy code. Sometimes, changing one line of legacy code is equally difficult to totally rewriting the entire stuff. But management doesn't think that. And so what they think you should do is bung it in a virtual machine and don't mess with it. Right. I'm now going to just talk a little bit about complexity, because I used to be a physicist. And here are some sort of numbers that you can have in the back of your head. The mass of the Earth is 6 times 10 to the 27 grams. The number of atoms on the Earth is 10 to the 50 atoms. And the number of atoms in the universe, well, the observable universe, is about somewhere in the range 10 to the 78 to 10 to the 82. That's the total number of atoms in the universe. Excuse me, it's a very big number. Okay, so let's solve a little equation. Here, I'm going to solve the equation. 2 to the k equals 10 to the 50. Right, we don't need Mathematica for that. We can do it in Erlang. Sorry, Stephen. K is 50 log 10 divided by log 2, so K is 166. Right, so 166 bits. 2 to the 166 is equal to the number of atoms on the planet. And if you divide that by 32, you get 5.18. And round that up, you've got 6. So what's that telling you? 6 32-bit integers in C. The number of states they can possibly be in is the same as the number of atoms on the Earth. Right. So if you wanted to test your program by computing all combinations, it's going to take a long time. Right. And we can work out how long it would take. Don't ever ask me about JavaScript, because it's only 3 variables in JavaScript. That's about the number of states that 3 variables in JavaScript could have is greater than the total number of atoms on the planet. Right, just think about that. Right. So a computer is a finite state machine. Right? It's got state. But how many states has it got? Well, it's got an awful lot of states. Okay, so a finite state machine is a state cross event, and you get a new state. And so the number of states that my little laptop here has got 250 gigabytes of flash memory on it. So the number of states it can be in is 2 to the 250 giga times 8. Right? And the number of atoms in the universe is, say, about 2 to the 260. And that means you need 2 to the, whatever that number is, it's unreadable, universes to find 2 computers that have the same state. Right? So this explains, this gives you a very good explanation to why your programs don't work and why Google... Because what happens is you download something onto your machine, and you do something, and it doesn't work. So you Google, and you find something, and it says, oh, I had exactly the same problem as this. Do this. And then there's like 10 mails after say, gee, thanks, that's really great. And so you think, I found it. And you do the magic spell, it doesn't work. So you Google again, and you find another mail that says, I had exactly the same, and it's the same story. And you do it again and again and again. And then finally it works, and you don't understand why. Okay. So why did it work for this guy but not for me? Well, it's because our machines were in a different state when we performed those operations. And the number of possible states of the machine is a whacking great big number. And I'm just not going to find somebody who's got a machine that's in the same state as mine. It's going to be in a different state. And that's why it's not going to work. Right. So what are we going to do about this? Well, there's all this math stuff, functional programming, scary stuff. We could try and prove programs to be correct. But that is way... That can deal with programs that are very small, not with the size of programs that we have today. Another thing we have to deal with failures. Computer systems fail. They're just going to fail. We have to deal with it. We can't ignore it. And this is to handle failures. We need to go into territory that is unusual. To handle failures, you need 2 computers. You might need 10 computers or 50 computers. You can't handle failures on one computer. If you've got a program executing on one computer and it fails, you're screwed. You need 2 computers or 100 computers. If you replicate something over 100 computers, and the chance of one of them failing is 1 in 1,000, then the chance of all 100 failing at the same time is 1 in 1,000 raised to the power of 100. So you can make systems that are almost incredibly reliable, provided you can replicate things and keep them independent. But in order to do that, you need to understand distributed programming and parallel programming and concurrent programming. You see, you can't, this leads you into this territory. If you're running programs on 2 machines, you are writing distributed programs. They run at the same time. That means you're writing concurrent programs. So you need to understand this. This leads you into territory. This is places you don't want to go. So it's quite easy to make things that are not fault tolerant and not scalable. But if you want to make things that are fault tolerant and scalable, you need to go into this strange territory. And there's some very good books, actually, that can help you. Yeah, hope they've got it outside. It tells you how to do this. So systems we build should self-repair, self-configure, and evolve with time. They should be more like biological systems. Languages, yeah, this is another problem. People say notation doesn't matter. They don't like Erlang's notation. It's got curly brackets and funny symbols, and they think it's not like Java. It looks different. But notation does matter because the Romans, they weren't very nasty if you had to do arithmetic. I was actually thinking of writing a program to do prime number of arithmetic, RSA in Roman numerals. I thought would be quite fun. You have to do that as an exercise. Languages do matter, but the problem is, in 1985, I think all programmers knew shell scripts and make and C. So there was a sort of lingua franca. We could talk to each other. All programmers could talk to each other. Actually, they couldn't. That's a lie, because there was another lot who knew COBOL. We didn't talk to them. they were already the sort of cliques. Oh, we did code. Oh. And there was the other lot, Unix and C and stuff. Make shell scripts, make C. Well, now, we don't have these common languages which we can talk to each other. You know, there's doobie doobie doo and Futran and Ruby doobie and grunt files and... It's funny when I tweeted and I say, oh, my grunt file doesn't work. Another tweet came back, Joe's gone over to the dark side. So I had to tweet uninstalling grunt later after I'd removed the nasty little thing from my machine. So it was, right, so when I learned to program, you could choose between these three languages. And now, well, I don't know how many there are. When I first made the slide, I found somewhere there were 676 programming languages. Then I found another slide, it's in 2,500. And I haven't a clue what most of them do. That's very difficult if you're a beginner. Which language do you choose to start with? There are so many. Right. So we don't have this lingua franca to talk with. And we don't have the build tools. We used to have make. Everybody had make files that were great. And now we've got ant, grunt, make, rake, malvern, jake, break, bit, bake, fabric, paper, shovel. And I checked on the net, and I found this, is there a rake, that was a lovely question. Is there a rake equivalent in Python? Well, you can use pava, invoke, shovel. Oh, I don't know. Who cares? Another thing, these build systems, I was writing an Erlang program at work for Ericsson. In anger, and I'd written 3 or 4 Erlang modules and had to go into an embedded system. And the guy says, oh, there's a script that does that. It was actually a make file that invoked a bake file, or a bit bake file, and it was taking rather a long time. And then I stopped it after a while. It had downloaded 46,000 files. Hang on, I've got 3 files. What's happening? Do you really need to recompile the entire Linux kernel and GCC and everything and build it? Oh, yeah, we do. Then I know I should have used grunt or something, and it would have been much easier. So without Google and Stack Overflow, programming would be impossible. How many of you can program without an internet connection for more than 5 minutes? Well, the rest can't. It's terrible. It's terrible. Right. And then we've got this sort of dichotomy between efficiency and clarity. You know, to make something clearer, you add a layer of abstraction, and to make it more efficient, you remove a layer of abstraction. So it's kind of, what should we do? So go for the clarity bit. You don't worry about efficiency. Wait 10 years and it'll be 1,000 times faster. If you want it 1,000,000 times faster, wait 20 years. It's quite easy. Doubles in speed every year. So right. Yeah, just wait a bit. Names. Oh, I don't like names. I'll talk about names. Names are very imprecise. We don't. Unless we can agree on the meaning of names, we get in a mess because we can't talk to each other. I'll say much more about that later. I'll get onto this bit now. How do I do for time? Yes, we're doing all right. So what do the laws of physics have to say about computation? I sort of got into this when I was looking at the manual page for Erlang, and it said, generates a unique reference. And then it says, will reoccur after approximately 2 to the 82 calls. 2 to the 82 calls is about 10 to the 25. You'll remember that number, 10 to the 25. Remember the number of atoms on the Earth's 10 to the 50, so it's quite a big number. Right. So here's some bits, I'm an ex-physicist. I'll just remind you of some laws of physics. Causality. A cause must always precede its event. Right? Something happens and something happens later because of it. And how things happen are because we propagate rays of light or sound or something. We don't know that something's happened until we get a ray of light or something that's conveying information to us. Okay. Now, a lot of systems actually breaks the laws of physics. So this notion that you can have consistent data in 2 different places breaks the laws of physics. It's the Byzantine general problem. If I know something, suppose there are 2 computers, and I say, hello, the value of x is 5. And then, does it know that? Can I assume that it knows that the value of x is 5? Well, no, because I don't know if that message got there. So I want him to send a confirmation back. He'll send me a message, yeah, I know that x is, he'll send me a message back, yeah, I know that x is 5. Can this computer now assume that I know that x is 5? And well, no, he can't, because he doesn't know that message has got there. So he won't know it's got there until I send him another message to say that it's got there. And that's the Byzantine general's problem. So you can't actually replicate data because you have different knowledge of the system at different points in the system. Despite this fact, we build systems with two-phase commit and forget about that. If you've got two-phase commit, yeah, it works. Well, two-phase commit breaks the laws of physics. So it's not very good. And then physics is all about things like concepts like simultaneity. I mean, if two stars explode in the universe somewhere, the guy sitting halfway between them will say that A and B exploded at the same time, and if the guy to the far left, he'll say that A exploded before B, and the guy on the far right will say B exploded before A, because it depends upon the time that light takes to reach these things. So if we forget that fact, especially when we're building distributed systems, we get into big problems. We shouldn't write systems that violate laws of physics. Yeah, that's a slide. That just says that. Entropy. So another law of physics. The law of physics says entropy always increases. What's that mean? It means, if you've got a load of dice, chuck them all up in the air, they're not all going to land with 6 upwards, or 1, or something like that. They're going to get more and more disorganized as time goes on. And that's what happens to software. The entropy of the software increases. And there are some fundamental limits to the speed of computation. Here's a couple of physicists. Who knows who the guy on the right is? No, left. Well, left if you look at it. Who's that guy? Max Planck, yes. So this is Planck's law. It relates energy to Planck's constant and a frequency. And the hairy guy, that's Mr. Einstein. He said so Planck said E is h mu, and Einstein said E is equals mc squared. And so Hans-Joachim Brechtken put these two numbers together and said, well, okay, so h mu is mc squared. So mu is just mc squared over h. And that's called the Bremerman limit, and it's 1.36 times 10 to the 50 hertz per kilogram. And that says that's the quantum limit to how fast a kilogram of matter can change state, how fast it can vibrate. So if you've got a kilogram, it can vibrate that quickly. So if you look to quantum mechanics, you'll find all these fun numbers. You'll find the Bremerman limit, the Margolius-Levintine theorem, the Birkenstein bound, and all that. So let's look at some of these. See, the Bremerman limit, that's the fastest clock rate that you can get out of matter. It comes from quantum mechanics, and it's 1.36 times 10 to the 50 hertz per kilogram. Then you've got the amount of energy that you can get. You can do 10 to the 33 operations per second out of a joule of energy. You can store 2 times 43 bits per mass m radius kilogram, whatever that was, and the Landau limit, the minimum amount of energy to change 1 bit of information. These come from quantum mechanics. Right. Oh, no. Just because of that, you could work out that a zettajoule is actually a 10 to the minus 21 of a joule. And a watt is a joule per second. And a Facebook data center is 28 megawatts, which is 28 times 10 to the 6 joules per second, which is kind of, let me see, it's 27 orders of magnitude bigger than the smallest amount of energy you could use, which is not very good. So now we want to build a really fast computer. So how do you build a really fast computer? You squash the components into the, you put more and more components into the box, and we limit the weight to 1 kilogram. We squash more and more stuff into it, so ultimately it just becomes a 1 kilogram black hole. That's the ultimate computer. That will actually it will operate at 10 to the 51 operations per second. Right, and it's got a size of 10 to the minus 27 of a meter, but there's a problem with it. It lasts for 10 to the minus 21 of a second. Right. And it emits data through Hawkins radiation and quantum entanglement. Right, so we don't actually, so it's a kind of fun thing. There's a picture from a Scientific American article. You drop a pair of, you've got your quantum computer, you drop a pair of particles into it, and the computation takes place inside the black hole. And then through quantum entanglement, the particle that's on the outside flips its spin or whatever you're measuring, and you've got the information out. So you've got to set up this thing that can measure what did I say? Let's go back. It's got to measure, you know, you've got to get this 10 to the 51 operations per second going. And then we've got to store all this stuff with quantum entanglement. And yeah, I don't think it's going to work for a while. I think we've got to learn a lot more before we can make this thing work. So if you're interested in that kind of thing, a very nice Scientific American article on the physical limits to computation. So why do we want to know these numbers? Well, one group of people, oh, wait a minute, I have a summary of these. So just summarize this. A 1 kilogram computer can do 10 to the 51 operations per second and store 10 to the 31 bits. And a conventional computer can do 10 to the 9 operations and store 10 to the 12 bits of information. So you see there's a big gap between what's physically possible and what we can do today. Of course, perhaps the ultimate computer isn't the 1 kilogram black hole. It's the entire universe condensed into a black hole behaving as a supercomputer. And it actually, in this article, you'll see that the universe, the entire known universe, has done 10 to the 123 operations since it was booted. So when the universe was booted a few years ago, it's now performed 10 to the 123 operations. So who's interested in this number? Cryptographers. So if you want to make a crypto system that is uncrackable, if it takes more than 10 to the 123 operations to crack the code, even with a quantum computer, because this is a quantum computer, you're going to need several universes to crack it. Right. Okay, so that was the physical limits of computation. So let me see. Yeah, we're on time. So what can we do? How can we sort out all this mess? So now I'm going to go into uncharted territory. Well, I want to build the entropy reverser. This is a device that we, can you imagine, I try to find a big sausage machine where you put sausage meat, you know, you turn the handle. So we put all programs into it, and we turn the handle, and a smaller number of programs come out. Then we can throw away all the other programs. And that breaks the second law of thermodynamics. Trouble with software, you see, complexity increases with time. We start with one program, and it splits and becomes 2 programs and 4 programs. We want to reverse that process. And this is a problem I've been thinking about for many, many years. I'll show you some of the conclusions I came to. Okay, so there are all sorts of problems with things. Files and systems, they mutate all the time. They grow in entropy. Disks are absolutely huge. And there's all these problems with naming. Naming's horrible. If you've got a file or something, what file name should it have? What directory should I put it in? Can I find it later? I program Erlang a lot. I write about 3 modules a day. So in a year, I write about 1,000 Erlang modules, and I've been doing that for 25 years, 30 years or something, 25 years. So I got like 25,000 Erlang files that I've written on my machine, and then I've downloaded. So when I checked, I had like 85,000 Erlang modules on my machine. Is that 85,000 different things? No, probably not. It might be 5,000 different things. I would like to take this 85,000 things and put them into something and turn a big handle. Out would come the irreducible kernel of that, the 15,000 things or 5,000 things. So I need to figure out how to do that. So the first thing I want to do is abolish names and places. Right. So to talk about things, you've got to have names, or you have to references to them, or some kind of name. So if you've got just a paragraph like that, cup of tea, he sat down, and a buttered slice of toast. It's difficult to refer to that. Okay, it's paragraph number 46,000, or no, paragraph number, I don't know, 412 from James Joyce's Ulysses, but that's a rather opaque reference, rather difficult to follow it up. But it's quite easy. We can just compute an SHA-1 checksum of it. So if you were talking to your friend and you said, I was reading this really great book. Said, yeah, what was it called? Well, it's called 78519AD1438. Well, you know, and then you would know exactly what he was talking about. There'd be no problem at all. If you believe in SHA-1, that is. Do we all believe in SHA-1? Yes, you know, it's like a religion, or MD5 or something like that. And then somebody said, no, it's been broken. Well, I don't care, I believe in it. Well, it's good enough. It's good enough for this. Right. Okay, so we've got this number thing. How do we find it if we've got this number? Well, URIs, they're sort of bad things. That's an address, you know, www.foo.ab. Well, why is it bad? Well, it needs DNS, and you can spoof DNS, and the host might be unavailable at the time when you want to get the thing. And if you change the thing being pointed to, the reference is wrong, and the reference is somewhere else, and you can't cache it. Well, you can cache it, but you don't know how long to cache it for. And if you request that, a man in the middle might change it before it gets to you. So you really don't want something like that. So what do you want? Well, if we went away from URIs to hashes, you just say, okay, get me that thing. That's a URL. Okay, you're not going to, that'll be embedded in some other document they've got in the file. You just be a link, you click on it in your browser or something. The nice thing about that, this is a content addressable store, is you haven't said where it is. Okay, and you don't need any form of security. I mean, a man in the middle could change the content, but you can validate when you get there. You say, go get that thing. You get this blob back. You compute its SHA-1 checksum, and it's the same as what you wanted. And therefore, a man in the middle cannot have changed it. And you don't need secure sockets or anything like that for that reason. You can't damage that content. You have no problem choosing a name. You just take it and you run the SHA-1 checksum on it, and there you are. And you can cache it forever. Right. So that's very nice. So then the only question is, how do you find that thing? Well, there are algorithms like Chord and Cademelia, and this is well studied. Okay, so for those of you who don't know, it's one of my favorite and most beautiful algorithms. Is you just take IP addresses of machines, that's the IP address in the right-hand column, and you compute SHA-1 checksum of that. That's in the left-hand column. You sort the SHA-1 checksums. These are now in a sorted order. And you say, okay, so which machine am I going to find that paragraph whose SHA-1 checksum? Well, suppose the SHA-1 checksum was, 4, 6, something or other. I just look in that list, and now I find two machines that bracket that. One IP address is lower and the other is higher. So I just send a message to those machines and say, excuse me, they're also going to have a table like that for the machines they know about. Okay. And so they send back to this machine an updated list of that, and we can refine that address down and down and down until we narrow it down to a small number of machines who the hash of their IP address is very close to the hash of the thing you're looking for. Okay, and that's called Cademelia. And it's the basis of the peer-to-peer system. So this is actually combining sort of the ideas from Git and BitTorrent. The BitTorrent trackers and the DHTs that are used for that are based on things like Cademelia and Chord, and these are self-organizing distributed hash tables. The idea of using hashes to identify things is widely used in Git, and is, so when you combine the two, you get GitTorrent, which is. I got very excited a few months ago. I thought, oh, if we combined Git and BitTorrent, we'd have GitTorrent. So I immediately went in, I'll register the domain name GitTorrent. Found two other people, there were two other projects already doing it. So, there's no such thing as a new idea. Okay, so let's start using these, let's start making the condenser. Well, the first bit's easy. Find all identical files. Right, so how do we do that? Yeah. For F in all files on the planet, do. C is the content, key is the SHA-1 checksum, store the key content in a distributed global file store. That will condense all identical copies of things to a small number of copies. That will reduce the total number of files. Right. That will run Because it's a distributed computation, everybody does it on their own machine. It will run very quickly. If we were to set up an infrastructure like this, we could collapse the total number of files on the planet to a small fraction of those that they actually are at the moment by condensing them down into this store. That's easy to do. The next bit is much more difficult, and that is to find files that are similar to a given file. So this is a problem that I've been thinking about for 20 years or so, and I've made embarrassingly small progress on it. I have back in my head this idea of a thing that helps me, and I've built one or two of them, and some of them work and some of them don't. So the idea is, it's rather like Twitter. You have a little box. When you have an idea, you have a little box, and you type something into the box. And I've done this, I've implemented it. You have a little box, and then there's a little icon, Sherlock Holmes, at the bottom. You type the stuff into the box, and you press the Sherlock Holmes button. And the idea is that will find, among all my files that I'm interested in, the most similar thing to what I've just put in this box. So I want it to find the most similar thing to this new thing. And then I want to know, is it different? So once it's found them, it makes a list of them in order, and then I can look at them. And then I can make a decision. Is this actually a new idea? That would be great if I had a new idea. That would be fantastic, you know. Or is it an idea I've had before and just forgotten about? Or is it an idea that somebody else has had, which I don't know about? So once I've found these other things, I can then make a decision if it's a new idea or if it's similar to them. And if it's, of course, what do I want to do now? If it's a new idea, that's fine. If it's similar to an old idea, I might want to edit the old idea and I want to merge the two together. So slowly we can start to condense the amount of information. So there are various ways of doing this. One which I'm currently playing with is called least compression difference. It's a very it's kind of nice. How do you know if two things are similar? If A is similar to B, then if you compress A and work out the size of it, and then you concatenate A and B, and you compress A concatenated to B, and look at the size of that, and if A and B are very similar, the compression algorithm should, if it's a decent one, produce something that's only slightly larger than A compressed. If B is identical to A, then when you compress A plus B, the compressed A plus B should only be a tiny bit bigger than A, because the compression algorithm will find all these sort of similarities. That's true for small data structures, but it's not true for big data structures. And for programs, it's worse because two things could be similar, but they're sort of isomorphic, but you've changed all the variable names and the function names. You still want to find the similarities. There are other methods. There's latent Dirichlet allocation, there's Bayesian inference, there are all sorts of techniques. The trouble is, you know, the algorithm was, I had the algorithm here. Yeah, oh no, find all identical files. It's for all files on the planet, compute this thing, using least compression difference. It even takes it takes minutes to go through a few hundred files doing this, because it's got to compress everything and do it. So if anybody out here, wants to work on something for the next 40 years and figure out how to do this, please go ahead, because we really need to reduce the complexity of everything we've been doing. Right, so we've made all this mess. Dijkstra said that computing was about controlling complexity, and we have failed miserably. Okay? I think one way to do that, I think about 128 kilobytes of stuff is about the limit to what the human brain can do. The only way to make reliable systems and modular composable systems is to make them out of small units which we can validate and then connect them together. So I think we know how to do it in a way. We actually need to reverse entropy. We need to do the opposite of. You see, GitHub is sort of cloning off things, and it's getting bigger and bigger. We need mechanisms to make things smaller and smaller. Quantum mechanics does set these kind of upper bounds on what is possible. So when we're figuring out the complexity of algorithms, we need to be aware of that. And we also need to be aware of the state space of what we're doing is enormous. And that's why, if we relate the complexity of a program to the number of atoms on the planet, we'll see a very, very small program has as many possible states as the number of atoms on the planet. You know, it's just enormously complex. We need to abolish names and places and replace them with hashes, and we need to set up global distributed hash tables and things like that. And then we need to make lower power computers that don't do environmental damage. We don't really want to fry the planet in answering all our questions. We need to make these carbon neutral, powered by solar panels and things like that. We need to get down the energy of computation. Computers are becoming a big environmental threat. They're using more energy than air traffic and things like that. And this is something, well, we can probably do without, well, no, we need both air traffic and we need computers. One is capable of going down to very low energy, the other is not. And computers can be made to operate at extremely low power. We need to do so with a degree of urgency. So that's what we've got to do. We've got to clean up the mess we've made. Thank you.